It's working now, sir.
Now it is working.
Should I start recording?
Yeah, start.
Should I start recording?
So hello everyone. Today we have this final talk of the second trimester on modularity and the generalized Fermat equation. And we have among us Professor Imin Chen from Simon Fraser University to speak on the Darmon's program part 2. So over to you, Imin.
Great, thanks. And it's a pleasure to be here. Thank you for the invitation to give a talk in this wonderful program. So my talk today will build on the talk by Angelos Koustianos, and I'll be talking on Darmon's program. And so more specifically, I'll be focusing my attention on generalized Fermat equations of the following form. So x to the r plus y to the r equals a cz to the p. So here r will be a fixed prime greater or equal to 3, and c will be a fixed constant. And the prime exponent p will be the one that's varying. And so our interest is to resolve equations like this for integer solutions in x, y, and z, which are mutually co-prime. So for instance, one might like to show that if p is sufficiently large, that this equation has no non-trivial primitive solutions. And so for this type of generalized Fermat equation, I'll refer to that as signature RRP. A very nice thing is that we have at our disposal many choices of Frey varieties, which have been discussed in the previous talks on the modular method. So first of all, we have, for instance, the Frey elliptic curves, which were constructed by Nuno Freitas in his thesis. We have Frey abelian varieties, which were introduced by Darmon when he wrote his article on his program. And thirdly, we will introduce a new hyperelliptic curve realization of some of Darmon's Frey abelian varieties. And this hyperelliptic curve construction was originally discovered by Kraus. And so the main theme of this talk is that if we combine information from the first two types of Frey varieties, and using ideas from Darmon's program, we can tackle equations of signature RRP much more efficiently. And I'll try to explain this in the examples of R equals 7 and 11. And before I forget, this work is joined with Nicolas Billerey, Dieulefait, and Nuno Freitas. So maybe it's good to recap a little bit the construction of Freitas's Frey elliptic curves for signature RRP. These were introduced in his thesis. And these are elliptic curves which are defined over subfields of Q zeta R plus. So the maximal real subfield of Q zeta R, where zeta R is a primitive R through to unity. And I think Nicolas' talk already mentioned these curves. There are roughly two categories of Frey elliptic curves that he constructed. One class depends on 3 parameters and another class depends on 2 parameters. And a nice feature is that in certain congruence classes, if for R, the elliptic curves are actually defined over proper subfields of this totally real field. So for instance, if R is congruent to 1 mod 6, or if R is congruent to 1 mod 4 in this case, and in this case, we get that the base field can be descended to a smaller field. And as you know from the modular method, that gives us a lot of advantages in terms of the computation in the elimination stage and the final contradiction stage. How did he construct these Frey elliptic curves? Well, the idea is to take the polynomial x to the r plus y to the r, factor it over the cyclotomic field, and select quadratic factors which are defined over q zeta r plus. So in particular, we would take a factor like this, and then the factor associated to its conjugate, complex conjugate, and consider also the polynomial x plus or minus y all squared. And by making a delicate scaling of these quadratic characters, we can find a solution in polynomials x and y homogeneous to the equation a plus b equals c. And then we just plug that into the usual Legendre elliptic curve Frey construction. So that's the basic idea of his construction. So let's maybe look at some examples. I'll give some examples for r equals 7 and r equals 11. For r equals 7, if we take the first category or type of Frey elliptic curve, we get actually an elliptic curve over Q. And this is what it looks like explicitly. And I'll note here that in the modular method, one typically wants the discriminant to be a pth power, and p being that prime exponent that is varying. That will be the case because the discriminant involves the 7th cyclotomic polynomial. And if we go back and factor this, it'll factor as x plus y plus the 7th cyclotomic polynomial, then using usual descent and assuming class number 1, we get that the discriminant is essentially a pth power. However, this discriminant doesn't involve the factor x plus y, and that has a bit of a disadvantage because it won't be able to detect the solution, the trivial solution 1 minus 1, 0. However, if we go to the second category of Frey elliptic curves, here we can't descend to a smaller field. It's defined over q zeta 7 plus. But another advantage, an advantage of this elliptic curve is that when we look at the discriminant, there's this factor of an a plus b. So if you plug in the trivial solution 1 minus 1, 0, it becomes a singular elliptic curve. And that means this Frey elliptic curve is sensitive to that trivial solution 1 minus 1, 0. And that allows us to get information about solutions avoiding that trivial solution. What kind of results can we obtain using only Freitas's Frey elliptic curves? Here are some sample results. Here the results are for r equals 5 and r equals 13. And I'll note here, as we've seen in the previous talks, that the modular method does have some essential obstructions. And in this particular case, it kind of manifests itself as follows. So if you look at the solution where xy is equal to 0, that actually gives rise to a Frey elliptic curve, which is not singular. And that would mean that in the modular method, it's very hard to prove that solutions are not periodically close to that solution where xy is equal to 0. However, as we saw, at least in the second category of for elliptic curves, it is sensitive to the solution 1 minus 1, 0. And by combining information from both Frey elliptic curves, it's possible to prove an optimal result. Optimal meaning we can resolve the equation for all the prime exponents that we expect the equation to have no non-trivial primitive solutions. And in this case, it happens to be all primes. There was one case that was not obtainable. That was the case p equals 7. And thanks to some help from Devendra, we also found some additional elimination techniques that work for that case. In fact, we found 3 distinct methods to solve this particular equation. Well, we have optimal results for r equals 5 and 13. What about 7? So already in Nuno Freitas' thesis, he had already proven an asymptotic result. This is a result where we show that the equation has no non-trivial primitive solutions for p sufficiently large. As it happens in this case, the sufficiently large is really big. And let me explain why. So in applying the modular method, one finds that to resolve all the cases, like we did for r equals 5 and 13, some of the levels of the spaces of Hilbert new forms are not practical to compute. And this is coming up in the elimination phase where one has to compute all of the Hilbert new forms at that level. And instead, what was done is to compute the subspace of rational Hilbert new forms, and this was done by John Voigt. And that allowed Nuno Freitas to eliminate those new forms of the rational Fourier coefficients. And then for the remaining new forms, which have non-rational Fourier coefficients, a Chebydarov density theorem or argument was used. And that's the reason why we have this in fact, the constant is very, very large. I don't even want to write it down, although it can be made explicit. So a natural question is, can we try to prove, is it possible to prove an optimal result for this equation? And what we did with my collaborators is to go through the modular method using the Frey elliptic curves that were constructed by Nuno Freitas and see what are the cases that we can do. And it turned out that, we can carry it out in those cases where the spaces of Hilbert new forms are not too large. And these are the 2-adic and 7-adic conditions which allow a proof which is optimal. And in this case, we expect for all primes that this equation doesn't have any non-trivial primitive solutions. And to deal with the remaining cases, just to give you an idea of the computational difficulty, one has to compute in Hilbert new spaces of dimension about 6,000. And throughout my talk, when I quote these dimensions, I'll be quoting the dimension of the new spaces. If you, of course, to compute the new space, you also have to compute the full space of Cuss forms. And that's, in this particular case, about twice as big. And computing the space of Cuss forms, typically the Hecke operators are sparse. However, once you go to the new space, that's where the sparseness is lost. And so even at dimensions around this size, at least with computers that are available to us, it is actually impractical to carry out the proof. So that's one question, and I'll keep that in mind for the last part of the talk. I'll answer and give a method that is inspired from Darmon's program to solving this question for all congruence classes, mod 7 and 2. And let's go to the case R equals 11. So one of Freitas's elliptic curves in this case has the following form, and it's defined over Q zeta 11 plus, which is a quintic extension of Q. So already that extension is rather large. And so if you try to carry out the modular method, once you get to the stage of computing Hilbert new forms, because you're working over this large degree extension of Q, of course, everything is relative, large is relative, but it is very, very slow and impractical. And I'll give some dimensions shortly. But another feature is that this is the second type of Frey elliptic curve. And so the discriminant involves an A plus B. So it is sensitive to the solution 1 minus 1, 0. And if one tries to use this Frey elliptic curve and try to, in this case, we're only interested in an asymptotic result for simplicity. And again, to get an optimal result, one has to do finer computations. But even to get an asymptotic result, one has to impose some two-adic or q-adic conditions on the solutions. And so one difference with this example as compared with the previous example, in the previous example, we put an example, a coefficient of 3, and that was to eliminate the solutions where xy is equal to 0, which still poses an essential obstruction to the modular method. For this equation, we chose not to put a coefficient, but try to impose some two-adic or q-adic conditions which avoid that trivial solution. And what we're able to prove is if 2 divides a plus b, or some prime not equal to 2 and 11 divides c, then we're able to resolve this equation under those two-adic or q-adic conditions. And the resolution in this case is a bit weaker. It's for p sufficiently large. A natural question thus is, can we obtain an asymptotic result for an 11-adic condition? And if you try to push through the methods, it turns out that you need to compute in a space of Hilbert new forms of dimension 12,000. So even, much, much bigger than the previous example. So in this case, it's quite hard to get even an asymptotic result under some 2-adic or 11-adic conditions. But again, the theme of this talk is later on. I'll explain how using Darmon's ideas from Darmon's program, one can answer a question like this. And so in order to get in to using the ideas from Darmon's program, let me introduce Kraus's Frey hyperelliptic curve for signature RRP. So as I mentioned, and was mentioned in previous talks, Darmon introduced Frey abelian varieties for signature RRP. So I think this was discussed in Anwesh's talk. These are constructed using it's a hypergeometric construction, or if you like, a super elliptic construction, and it's somewhat less explicit and something that we're less familiar in terms of working with. So for instance, when we're working with elliptic curves, we have Tate's algorithm, we can compute conductors, everything is very, very explicit. We have algorithms. So as a kind of step in between, it is useful to have a hyperelliptic construction. And this was first discovered by Kraus. And what we'll actually show is, or at least state, what we show is that taking the Jacobian of Kraus's Frey hyperelliptic curve actually gives a realization of Darmon, one of Darmon's Frey abelian varieties, but that's up to some transformation, which I'll explain shortly. And so I'll illustrate Kraus's construction in the case R equals 7, and with the constant C equals 3, just to be concrete. However, the constructions work for general R and general C. So here's Kraus's Frey hyperelliptic curve in this setting. So we set omega j to be a primitive seventh root of unity plus its inverse. And we form g of x to be the polynomial with roots being omega j. And the hyperelliptic curve is given explicitly by this equation. Okay. And in terms of the application to the generalized Fermat equation in question, we set this parameter s to be this expression in that non-trivial primitive solution. Then after our quadratic twist, we can move to an integral model, and it has this very nice form, an explicit form like this. And we see you can compute the discriminant, and because it involves a c, and a to the 7 plus b to the 7 factors is a plus b, plus the 7th cyclotomic polynomial. And so that means that this discriminant actually contains a factor of an a plus b. And so it's also sensitive to the solution 1 minus 1, 0. So here's a proposition that summarizes the kind of the main properties that we need, at least the first few properties that we need of the Jacobian of this hyperelliptic curve. So the Jacobian is of GL2 type, and it has real multiplications by this totally real field Q zeta 7 plus. And furthermore, it gives rise to an odd Frey representation of signature PP7 with respect. So the points are a little different than in the usual definition of the Frey representation. Usually the points are taken to be 0, 1, and infinity, but in this case, it happens to be minus 2i, and infinity. And it's a little curious here that, I mean, the signature isn't quite what we want. We want the signature to be 7, 7p, but it turns out that if we make a transformation, so again, I'll just recall the Frey abelian variety constructed by Darmon. It's for signature 7, 7p. If we take an extension, and so this was a hyperelliptic curve over this function field, and we take this extension of k of s and another function field k of t, subject to the relation between s and t being this, then at most, over at most a quadratic extension, we have that the mod p representation of Kraus's Frey abelian variety coincides with the mod p representation of Darmon's Frey abelian variety, and therefore, under this transformation, this gives a realization, a hyperelliptic realization of Darmon's Frey abelian variety, which he constructed using a superelliptic construction. And that's useful because we do have more information about hyperelliptic curves than we do about superelliptic curves. If we specialize to the case of p equals 7, then we get a Frey representation of signature 7, 7, 7. And as was mentioned in previous talks by a classification theorem by Hecke, this has to arise from the Legendre family of elliptic curves. And so we have this very, very useful relation between the mod 7 representation of Kraus's Frey abelian variety and the mod 7 representation of the usual Legendre family of elliptic curves. And that will be used many, many times later in my talk. We'll see that it's a kind of a key relation that can be exploited for many results. So this is just restating that coincidence that the mod P representation of Kraus's Frey abelian variety coincides with that of the Legendre curve. And since the Legendre curve is, in this particular case, we're taking solutions which are integers, it is actually a representation that will extend to the absolute Galois group of Q. And furthermore, using this coincidence with elliptic curves, and because we have a lot of information about the mod P representation of elliptic curves, we can prove that the mod 7 representation of Kraus's Frey abelian variety is absolutely irreducible and not projectively dihedral, unless we're in some small cases. And that is the first step to allow us to prove modularity, because we know by Serre's conjecture or by modularity of elliptic curves over Q, we know that the right-hand side is modular, and that shows that this residual representation is modular. And then using modularity lifting, we show that the p-adic representation or the 7-adic representation of J is modular. And so let me talk about a rather general modularity lifting theorem of Billerey and Darmon. And again, this will be used not only to show modularity of Kraus's Frey abelian variety, but also to give a refined level lowering result. So as you recall from the proof of Fermat's last theorem, a crucial step was Ribot's level lowering theorem. You can think of this modularity lifting theorem as a merging of modularity lifting as well as level lowering. And I'll kind of explain that as I explain the theorem. So it applies for a totally real field. Let P be a prime. Suppose we have a residual representation, and let's assume the residual representation is modular. It has cyclotomic determinant, and it is absolutely irreducible. In the case P equals 5, there's an additional technical assumption. So for all the places where the residual representation ramifies, and including the places above P, I'll prescribe a finite set of these primes, which contains at least these ramified primes and the primes above P. For each place in this finite set of places, we'll choose a Veidelian type. That is, we'll look at the residual representation and restrict it to a local decomposition group at this place of S. And we'll make the assumption that it has a nice lift, a nice p-adic lift with a prescribed Veidelian type. And on that assumption, the theorem says that there is a lift, a global lift of this residual representation unramified outside S, such that the global lift locally has the prescribed Veidelian type for all places in S. And moreover, any such lift is modular. And so by prescribing these Veidelian types, it allows you to prove modularity lifting as well as level lowering. So I haven't said what nice means, but at least in the cases that we're applying it to, in this particular case, it's the 7-adic representation attached to J. The condition of being nice will be satisfied. And so it's kind of a long technical list of conditions, but this is just a summary of how we use this result. And this allows us to prove that Kraus's Frey abelian variety is modular. And the proof is, as I mentioned before, I mean, there's some small cases where it has complex multiplication, in which case it is modular. Otherwise, because we have irreducibility, absolute irreducibility, We can apply the modularity lifting theorem. We have that the residual representation is modular because it arises from a residual representation attached to a Legendre curve, which is or extends to the absolute Galois group of Q, and using Serre's conjecture of modularity of elliptic curves. We have that representation of GQ is modular, and hence using cyclic base change, the residual representation that we want to lift is modular over K by cyclic base change. And then we apply the lifting theorem of Breuil and Diamond. And the modularity proof is fairly general just because the technology for modularity results is quite general by now. So it doesn't require C equals 3. We will have a condition 2 does not divide A plus B later in this talk, and modularity does not require that as well. But let me just say a few words about the proof of absolute irreducibility and not being projectively dihedral, since those were conditions that were used in proving modularity of J. And it's another illustration of how we use this relation between the mod 7 representation of J and the mod 7 representation of the Legendre curve. So assuming that the mod 7 representation of J is reducible, carrying this over, and this is all up to quadratic twist, but that doesn't affect the property of being reducible. That would mean that we get an elliptic curve defined over K, which has a 4 isogeny as well as a 7 isogeny, and hence also 14. However, the K rational points on the modular curve x0, 14 have been determined, and they all correspond to rational elliptic curves with a conductor 49. And none of these acquires a 4 isogeny over the extension K, which is a cubic extension of Q. And so we conclude that the original assumption that this was reducible had to be false. And there's some other arguments which use K totally real to get to absolute irreducibility. But that's, I thought I would mention that because we will be using this relation many times, and this is yet another example of that. I don't know if people have any questions, please feel free to.
This study over this modular curves over x0, 14, and 28. This
Oh yeah, yes.
Comes in your studies, or it was done before in some general study? Okay.
I'm sorry, I didn't get your
point
question.
on these curves x0,
Yes.
x28, and x14. It was
Yes.
done by during this work, or it was
No. Yeah, I apologize. I don't know exactly who did that, but the best reference to look for that is Najman. He's been writing a number of papers on rational points over number fields of modular curves. Philip Najman.
Okay, thanks.
Yes, yeah, and he would definitely have all of the references back. But some of these things were studied a long time ago, a very, very long time ago. So like sometimes, there'll be some result that comes, from Kenku or Tamiane. Yes, that's right. Yeah. Oh, okay. So conductor. So one of the steps in the modular method is to compute Hilbert new forms at the relevant level. And to determine the relevant level, we have to compute the Serre level of the mod P representations attached to your Frey varieties. And that will be, in this case, rho bar of JP. And I think Angelo's probably gave some examples, but I'll do one example here just to give an idea in case you haven't seen his talk. So again, the Frey hyperelliptic curve in this case for this equation is explicitly given like this. There are unique primes above 2, 3, and 7 of K. And the Serre level of the Mod P representation of J is given by this. So it has conductor exponent 2, 1, and 2 at the primes 2, 3, and 7, above 2, 3, 7. And yeah, so the reason there are no other primes is that at the primes dividing C, the hyperelliptic curve has multiplicative reduction. And because of the fact that the discriminant is a p-th power, one can show that the mod P representation is finite flat or unramified. And hence, we can strip those primes from the Serre level. But let me describe at least the conductor calculation at the prime 2. And if this were an elliptic curve, we would just say, okay, well, let's put it through Tate's algorithm. But for hyperelliptic curves, one does not have a general Tate's algorithm in all characteristics. Although recently there have been some works by Dr. Chen and his collaborators for odd characteristic. So we proceed in perhaps a more ad hoc way, but it is a technique that is fairly efficient for computing conductors of hyperelliptic curves in families, right? You can think of this as a family of hyperelliptic curves in the parameters A, B, and C. And so we start with the initial model, and we make a translation so that the singular point at 2 is moved to the origin. And we're under the assumption that we're working over a field which has ramification index 7 over the completion at the prime 2 of K. And what we want to show is that over this extension, this hyperelliptic curve has good reduction. And then we also assume some congruence conditions that are mild, because we can always arrange the solutions to be in this case. So we make this translation. And after the translation, under these congruence conditions, these two-adic conditions on the solutions, it turns out the valuation of the coefficients of the model for the hyperelliptic curve are large. And because they're large, we can make this transformation. So pi is a uniformizer of that extension of ramification index 7. And we can make this transformation to get an integral model, which happens to have good reduction. And so it is kind of like a Tate's algorithm. However, we don't have a general Tate's algorithm for hyperelliptic curves, but we can carry out in this case. Another thing to mention is to compute these valuations of the coefficients, one takes the coefficients and expands them. So these are homogeneous polynomials, and so we can expand them in some parameter in order to determine the valuations here. Okay, and I shouldn't say that it's homogeneous. If you have some weights on the variables, then it becomes homogeneous. And so there's an easy kind of computational way to do that. However, one has to guess that this hyperelliptic curve attains good reduction over this extension, which has ramification index 7. And this is where an idea of Nuno Freitas comes in. Once we have a candidate field for semi-stable reduction, then we can match it using inertial types to compute the conductor. by determining what inertial type it has. And actually, it goes the other way. How did we guess this initial field? It actually came from the inertial type point of view. And but in this case, we kind of do it in the logical order that we want to prove it in. And so by class field theory, we know that there is a totally ramified cyclic extension of K completed at 2 of degree 7, which is obtained from the fixed field of a character of conductor 1. And since it has ramification index 7, we know that the hyperelliptic curve will have good reduction over this cyclic extension. And that means that the restriction of the lambda adic representation of J, so lambda is a prime above L not equal to 2 in this case, it becomes unramified over an abelian extension. And hence, if you look at all the kind of inertial types, the possible local representations into GL2 that this can take, it has to be a principal series representation, and hence given by a direct sum of 2 characters. We also know that the determinant is cyclotomic and hence unramified at 2. And so these 2 characters on the principal series have to be inverses of each other. We know that the inertia is non-trivial because of the ramification index 7. And hence that tells us that the chi has conductor exponent exactly 1. And then using the formulas for conductors of local types, we deduce that the conductor exponent of this lambda adic representation is 2. And then finally, the conductor is preserved after reduction. And so that allows us to compute, if I go back here, the Serre level of the residual representation, the mod P representation of J at the prime 2. And so we can proceed similarly for the other cases. Another ingredient in the modular method is irreducibility. We did show irreducibility for the mod 7 representation of J. However, in the method, we need to show it for general P, and P is a prime of K above P, P being the exponent of the equation of interest. And so here's one result. I won't go through it in too much detail. I think Angelos gave an example of this method of showing irreducibility. The main idea is the following: because 2 does not divide A plus B, we expect that J has, and we show that J has potentially good reduction at 2. And usually in the game of proving irreducibility, when you have potentially good reduction, you base extend to that field, which gives you good reduction. And then you can use local methods to prove irreducibility. So for instance, if the mod P representation is not irreducible, it's reducible, a matrix form will be given an upper triangular form with some diagonal characters. And we kind of tabulate all the information that we have. We know that the product of these diagonal characters is the determinant, and that's the Pete cyclotomic character. We also know the conductor of the left-hand side, and that puts restrictions on the conductors of these diagonal characters. And using, again, some local class field theory, we and also global class field theory, we can show that without loss of generality, for P sufficiently large, that one of these diagonal characters is unramified at every prime above P. And then we conclude by computation on Ray class groups of the relevant conductors of that unramified character at P. And then we get a contradiction. And So I think Angelos gave an example of that, but this is kind of a common technique for proving irreducibility on a condition like this. So my example was for R equals 7 and C equals 3. So in that case, we went through all of these steps, but as I mentioned, we can also prove these results for general R. So for instance, we can prove Kraus's abelian variety is modular in general. We also have conductor determinations for general R and irreducibility statements. And so here's one example of a general irreducibility statement. In this particular case, this condition that R doesn't divide the unit group of the residue field at the prime Q2 of K ensures that the local representation is supercuspidal, and hence automatically the global residual representation is irreducible. And so we have a number of these results, all of which are kind of useful for Dieulefait applications, and especially if you're interested in more general R. And so finally, let's go back to the first of my questions, which was, can we prove an optimal result for this equation? And in this case, an optimal result looks like for all, if you like, all prime exponents, but once you prove it for all prime exponents, it's proven for all integers greater or equal to 2. So I'll first mention that the reason why one was not able to prove an optimal result was that the conductor of the Frey elliptic curve was too large, and computing the Hilbert new forms at those levels was not practical. However, we have a new observation in our new work, which is the following. If you look at the image of inertia at 2, and that is relevant for the conductor exponent at the prime Q2, it has a very large inertial image, SL2F3. And so by twisting the elliptic curve, the Frey elliptic curve, one can't reduce the size of the image of inertia. However, it turns out, and this is something that we had noticed in our recent work, that it's still possible to twist the elliptic curve so that the conductor is reduced. So the conductor goes down from something like 4 to 3. And now the computation is in a space of dimension 818, which is actually feasible computationally. It takes a while, it takes about an hour to do the computation, but it is now possible with this observation to prove this optimal result using Nuno Freitas's elliptic curves, E and F, the two classes of Frey elliptic curves that he constructed in his thesis. Now, what happens if we've developed all this machinery to use Kraus's Frey abelian variety? What if we now allow ourselves to use also, in addition, use Kraus's Frey abelian variety? So we won't, we still need to use Nuno Freitas's Frey elliptic curves, but we don't need to use it in the cases where the level is high, where we have to do that computation of 1 hour of computing Hilbert modular forms. And so in particular, we can use the Frey elliptic curves to prove that it suffices to deal with the case 7 divides A plus B and AB even. If AB is even from the form of the equation, we can assume without loss of generality that 2 divides A and B is congruent to 1 mod 4 by switching A and B and possibly negating A and B as an ordered pair. And that's very fast because in those cases, the levels are very low. But now once we're in this situation, we can use Kraus's Frey abelian variety. And in particular, we're actually going to use a twist. Without observation on twisting, we now use that whenever we can to make the level as small as possible, even if it was not obvious that one could make twist so that the level was smaller. And so if you carry out the modular method in this situation, we get to a level like this. And now the space of new forms has dimension 104. And then we can do the elimination now using Kraus's Frey abelian variety. And of course, all of these techniques are within and inspired by ideas from Darmon's program. And using this proof where we combine all the Frey varieties that are available to us and optimizing their levels, this last proof only takes about 2 minutes in total time. However, it does require one additional non-trivial elimination technique, which is needed for the Frey abelian variety. And that also highlights an advantage of the Frey abelian variety. Now, certainly, computing with abelian varieties, Jacobians of hyperelliptic curves is harder than elliptic curves. But for the purposes of the modular method, that comes with some gains in some other parts of the method. And so we call this finer elimination for Frey abelian varieties. And so we see that the mod P representation of J arises from a new form at this level. And there's, the dimension is 104. I think there are 19 new forms. And sometimes if the Fourier coefficients are very in a field that's very large, that can take quite a lot of time. And there is some overhead in computing with hyperelliptic curves rather than elliptic curves. However, nonetheless, using this theorem of Billerey-Diamond, when we level lower to this level, it's possible to prescribe the inertial types. And we knew that the inertial type of J was principal series. And that allows us, we're allowed to prescribe the inertial type that is compatible with that on residual representations. And the theorem of Billerey-Diamond, now we're thinking of it as a level lowering result, allows you to level lower with a prescribed inertial type. But if one level lowers to an inertial type which is principal series, one can show, and this character has order 7, one can show that that implies that the field of Fourier coefficients of this new form has to contain K, which is, in this case, Q join zeta 7 plus. And so in the elimination phase, one can just throw away any new form whose Fourier coefficients does not contain Q zeta 7 plus. And that eliminates all but 6 of 19 new forms. So without any computation at all, one is now reduced to doing an elimination with only 6 new forms. And that's what allows us to give a proof in such a short time of 2 minutes, if we're allowed to use all of these Frey varieties together. And so let's go to the second question, which was, I guess it was an asymptotic result for x to the 11 plus y to the 11 equals z to the p. And that was under the 11 added condition, 11 divides a plus b. And just to kind of remind ourselves, if we try to use only the Frey elliptic curves, it requires computation in a space of new forms of dimension 12,000, which is extremely large, considering the matrices are not sparse in that space, in the linear systems that define these spaces. So what do we do? So we call this the method of Legendre descent, and it works as follows. I'll describe the general result, but it's called Legendre descent because it uses that connection with a Legendre curve. And in this case, we're using Kraus's Frey abelian hyperelliptic curve Frey hyperelliptic curve for R equals 11. We take its Jacobian, that's the Frey abelian variety of Kraus. We'll twist so that it has a smaller conductor at 11. And we're working over this quintic extension of Q. And the idea is that we can eliminate all the new forms at the Serre level, which have the property that the new form has irreducible mod 11 representation. And this is for P sufficiently large. And so like that other elimination technique where it was required that the new form has Fourier coefficients containing K. And here, the condition is that any new form whose mod 11 representation is irreducible is automatically eliminated for P sufficiently large. And the method works as follows. Let's assume the new form that we want to eliminate is irreducible, and we'll work towards a contradiction of P sufficiently large. So one thing we can ask is the mod 11 representation on this new form a base change from Q? And we can test that easily by Clifford theory. It turns out that it's a base change if and only if the inner conjugates of this representation are isomorphic to the original representation. So using a Chebotarev density argument, we can conclude that either it's a base change from Q, or we have that there's some prime and some conjugate prime such that the traces of Frobenius at these primes of the 11-adic representation are not congruent mod 11. And this is for some conjugate. And we'll get a contradiction. So first of all, we need to set things up. If Q divides C, then we saw from a previous result that we can use the Frey elliptic curve to bound P. And that is using a prime Q, which is not 2 or 11. So we can now assume that J has good reduction at Q. And then putting together all of these conditions, we get that we either get a bound on the exponent P, or the residual representation on 11, mod 11 representation on F is a base change from Q. Now, once it's a base change, we know it arises from a classical modular form over Q. And that modular form could have higher weight, but the weight is actually bounded because we have an 11 here. So the weight goes up, possibly up to P plus 1, which is 12. And so we can do this local elimination phase, which is usually it's done by a local comparison of traces using a computation of classical modular forms, which is much, much faster than Hilbert modular forms. And that's what allows us to prove this elimination result. And then finally to this asymptotic result, how do we use this elimination result? So if 2 divides A plus B, that's proven in this situation. So now we assume 2 doesn't divide A plus B. And that is interesting because you still need to use the Frey elliptic curve to get the argument started and get to a situation where you can use the Frey abelian varieties from Darmon's program. Certainly we haven't proven all of the steps of Darmon's program in general, but we've proven some steps. And by leveraging our information from these elliptic curves, we can kind of transfer it over and using the multi-Frey technique. And so that's an example of that here. So we know the mod P representation of the Kraus's Frey abelian variety arises from a Hilbert new form at this level or this level. Actually, we don't need this level here. I've just kind of stated the theorem in general, or the proof. We pick an auxiliary prime 23, which is totally split in K. And again, if Q divides C, we can use the Frey elliptic curve to bound P. Otherwise, we're in a situation where J has good reduction. And the idea now is that we show that it must be the case that the trace of Frobenius of J at the prime Q satisfies this condition. Because if it didn't satisfy this condition, so this condition looks like this representation. So this looks like the mod 11 representation attached to F is reducible, but we know that the ones which are irreducible, which would be in this congruence class, are eliminated by the previous theorem. And so arguing like that, we can assume that we have this congruence on the traces of Frobenius of J mod 11. And so we can do, again, a local comparison of traces. And we kind of observe, it's kind of a miracle. When you do the computation, it turns out that the traces of Frobenius take on only the following value up to permutation. And these values for the traces at Q, and it's actually up to plus or minus, are actually conjugate to each other. These are the full conjugates over Q zeta 11 plus. And using the fact that J is defined over Q, we get that if I conjugate this trace, it's the same as the trace for a conjugated prime. What that means is that the sum of all of these traces over all the primes of K is actually plus or minus 12. And then we can do, that means that there is a new form at this level. So now we're in this situation where the sum of all its Hecke eigenvalues over the primes of Q is plus or minus 12, but that's something we can check just using Hecke matrices. And that's on a space of dimension 376. And that just takes a few minutes to compute. And so that concludes the proof. And sorry, I went a little bit over time. Thank you for your attention.
Thanks, Professor Chen. If anyone has any questions. Perhaps not. So I have some doubts, in general doubts, like this is mostly we are following the modular method, right?
Yeah.
But Darmon in some other papers gives some other methodology to approach these equations more geometric, like this article on the 14th lectures on the Fermat equations. Have you seen it?
I haven't. So which equation is that?
14th lecture on the Fermat theorem.
Oh, okay. Are you talking about these M curves?
But and he suggests to study the Bailey curves.
Yes.
And
So, yeah. So Darmon has this very interesting paper that was. It was also all of this was quite early, shortly after the proof of Fermat's last theorem. I think it was something like Wiles minus epsilon or Wiles plus epsilon.
So that was the initial paper, and then he extended and modified after 6-7 years later.
That's an interesting. It's an interesting idea to kind of approach it using these covers, and he has. So he defines an object called an M curve.
Darmon, if you know Darmon.
Darmon.
Biker's student.
Who's student?
Fritz Biker's student.
Maybe you should tell me. Like, I don't recognize the name. No, but yeah. So I think it's a good way of viewing in an alternative way the problem of generalized Fermat equations. My feeling is that when you want to
that the study of the finite cosines of the triangle groups. would lead to the study, would be correspond to the study of different cases of.
Oh, Sander. Okay, thank you. Yes. Oh, yes, yes, yes.
So in the first chapter of his thesis, he
Yes.
compute some examples of the Bailey curves.
Yes, yes, yes.
But generally it is not followed. I think it is also very difficult to study Bailey curves.
It
and
is. Yeah.
Arithmetic properties. So yeah.
Yes.
But that is slightly different, this modular method, right?
It is a little different. So typically in that setting, it's Chevalier-Vey. And so the idea is that you have this cover, and it has this signature. And if you have a solution to a generalized Fermat equation, you lift it to a rational point using Chevalier-Vey with bounded degree, and then you use faultings. But typically those arguments are typically for fixed exponent. But nonetheless, that's very interesting, because even for some small exponents, it would be nice, like, in this case, like, can you do 11, 19 or 23, right?
Yeah.
Yeah. So those methods are more adapted for specific P. And Darmon's program is adapted for one parameter families. So one varying exponent.
I see.
And of course, you have Beal's conjecture, where all three exponents are varying. And I don't know of a technique, short of carrying out Darmon's program very, very precisely and not asymptotically, to the point that you can prove it for three varying exponents. But I don't know of a technique. There is one technique from, I think, a paper of Sek and another person, maybe Annie, where they deal with two parameter families of generalized Fermat equations. However, in that case, the exponents are not prime. So it's something, I think, special to the composite exponents. I don't know of a technique that can deal with generalized Fermat equations in more than two parameters being prime. Yeah.
I see, thanks. So I was just understanding, so this particular method that you people are adopted in these problems are completely different that studying the Bailey curves and.
Yes, that's right. There's also another technique that's closely related with the Bailey curves, and that's been used by Sander and Sik, which is there is a hyperelliptic curve, which is often attached, one can construct for signature RRP. And these are still different from the ones that Freitas constructed, because the ones that he constructed are adapted for the modular method. These hyperelliptic curves are not adapted for the modular method, but if you have specific prime exponents, like 7, 7, 11, you can write down this hyperelliptic curve. And then Samir is like an expert in computing rational points on hyperelliptic curves. And so you can use Chabot-T and all these methods to prove such things. You might need to use generalized Riemann hypothesis to get a rigorous proof, but yeah.
Okay, we will be discussing these things, so we will learn more about from your talk and in the future.
Great.
Thanks again. So
you're welcome, and thank you for inviting me to this wonderful program.
So we will be closing this meeting. Thanks.
Okay, see you later. Bye.
Bye.